Welcome to the AP Physics Workbook tutorial. This is on Unit 10, Mechanical Waves and Sound. The section is 10A, Properties of Waves. Here you could read the scenario to yourself. Part A asks us on the diagram, please label the crest, trough, amplitude, and the wavelength. The crest is referred to the highest point right here. And it stretches all the way from the equilibrium all the way to the highest point. This distance from the equilibrium or to the highest point can also be called the amplitude. And the bottom part is called the trough. This is going to be the lowest point. Please also understand that the amplitude can also be referred to here as well. This is one complete cycle of the wave. This distance for one complete cycle is going to be called the wavelength. On this diagram, it says to stretch a continuous wave with half the amplitude. That's mean. So right here, it goes up to 1, 2, 3, 4, 5. That's how high it went. So half of it would be right here at 2.5. So it would look like this. Same equilibrium. 2.5 down, up, 2.5, back to 0, 2.5, and here. This is when it's half that. Now it says to calculate the speed of the wave. The equation can be defined as velocity is equal to the frequency times the lambda wavelength. The frequency here is, let's say, 5 hertz. Right? And then the wavelength here is going to be 1 meter. Multiply 5 hertz by 1 meter, you get 5 meters per second. This is the velocity of that wave. If you're asking, how did I get that 5 hertz? Because right here it says she shakes her hands 5 times per second. That right there is the frequency. The next part of the problem, it asks us, on this diagram, stretch a continuous wave with twice the wavelength. All right, so here the wavelength, lambda, increases. What does that mean visually? I supplied you with these notes. Notice as the wavelength increases, so here it's going to increase. The wavelength here is going to increase. As it increases, do you see how it gets more stretched out? As it gets smaller, it gets compressed. So as it increases, it gets more stretched out. The wavelength is longer. So it's going to go up here, the same amplitude, right? Then it's going to go back down. Then it's going to go down here. Then it's going to go back up. Notice that originally there was 2 of them that occurred in the same time, right? Because the wavelength was smaller. So do you see how this was all the way here, was the original wavelength, lambda naught. The new one would be all the way from, you see, we would have to continue it, right? This would be the new lambda. Okay, the lambda new. You see, it's twice as long, all right? So it should look something like that, okay? Is Angelica shaking the string at the same rate? Right. This question has multiple parts, okay? The first part you want to think about is this. If the wavelength here increases, because it gets longer, exactly like what it says here, twice the wavelength. While the velocity remains constant, the frequency must decrease. That's how it looks like. For that to happen, you have to understand that velocity also depends on something else, the tension force and the mass and length of the string or the rope. Mu is equal to m over L. If you plug it in here, you can see that velocity can also be equal to the square root, the force of tension over mu. That's the substitution for m equals to L. This whole part here comes from these notes that you should take a look at. It says, the string on a guitar or violins are all the same length. They sound at a different pitch because the string has a different mass per length. Mu equals to m over L, which affects the velocity of the string. V equals to square root ft over mu. Thus, the velocity on a heavier string is lower, and the frequency will be lower for that same wavelength. The tension ft also has an effect. Indeed, adjusting the tension is the means for tuning the pitch of each string. That's why here the velocity can change based on these things. So these are the notes for it. On the AP exam, this whole worksheet for the last question is trying to get you to understand this idea. Okay? While examining the effects of tension in a string or a spring on a speed of a wave, students may not know how to control for the change in the length that goes along with the change in tension. You can simply allow students to address this as a source of error in your experiment. With more advanced students, however, you might want to go guide them through come up with the correction for the change in linear density using this formula. We use f of t for the tension here, okay? So v is the velocity of the wave, t is the tension, and mu is the linear density of the spring, okay? That is what this part is trying to get you to understand. So, for the wave to move at the same velocity as before, Angelica actually must decrease that ft, which is the tension force, which is achieved by her applying a smaller force on the rope. That's it. Okay? This part, so the first part, the answer is that she has the same rate for the continuous wave, because here it says that it remains constant. The V remains constant. Okay? This is the speed of wave. What you have here is this is the velocity of the person applying it. Okay? Because it says it right here. Right? What they're trying to get you to understand here is that the linear density of the string will change. For example, if the string is stretched to 1.5 its original length, its linear density is 2/3 as great. Okay? So, even though the velocity is constant in the wave, okay, the change in the increase in the wavelengths affects the tension force of the wave itself. Therefore, Angelica has to actually apply a different tension force to keep the wave at the same velocity. All right? There you go.